Finally, for some examples, in work example 6, we basically have 3 molecules with speed 2, 3, and 5 meters per second. So to find mean or average speed is basically summing the magnitudes of the velocity and then divide by 3. For mean square speed, what I'll do is I'll first square first and then find average. That's why you can see that I've squared 2, 3, and 5 first before summing them up and then divide by 3. Also, take note that the square of the mean speed, which is basically the square of the 3.3 meter per second, is not necessarily equal to the mean square speed, which is actually the average of the square speed. So in mathematical speak, what is the square of the mean speed is basically the sum of the speed divided by n, whole thing square. This is the square of the mean speed. Whereas the mean square speed, what is mean square speed is basically I'm summing the square of the velocity first divided by n. Okay, so these are actually two different mathematical formula, so just take note of them. And then for example 7, which is basically very similar question, except that I have 5 molecules from speed with speed from 100 to 500 meters per second, and we need to find the root mean square speed instead. So to find the root mean square speed, basically you square root the mean of the square, i.e. what you should do is you square first, and then you find the average, and then finally you square root. Okay, so therefore the solution is as follows. Please also take note that the average speed is 300, which is not the same as your mean square speed. And then for example 8, we have the mean square speed, which is basically the bracket c square of the molecules of the ideal gas at 27 degrees Celsius. So 27 degrees Celsius, you must take note that you need to convert it into absolute temperature, so at 273.15. Okay, given to be 3.7 times 10 to the power of 6 meter square per second square. And then we are required to calculate the mean square speed of the second type of molecule, where the second type actually have a molecular mass that is twice of that of the first type. Same thing, given in degrees Celsius, we need to convert it to absolute Kelvin. So the way to solve this kind of question is to make use of the relationship that the Ke is proportional to T. And at this point in time, you can make some assessment that I expect the mean square speed of the second gas to be actually smaller than the first one because it has a lower temperature. At the same time, it has a higher mass. So therefore, the mean square speed need to be much lower so that I can maintain the proportionality relationship. So the way to solve this kind of question is really just to take Ke of the second mass divided by K of the first mass to be equals to the temperature of the second mass divided by temperature of the first mass. And then all I need to do is just to substitute into the equation the values that are already given, and then I can find out the solution. So the common error for this particular question is that students forget to change the value given in degrees Celsius into Kelvin. So do take note of this kind of error and don't make them yourself. And then for example 9, we are given that the volume containing a given mass of the gas is actually reduced, but the temperature is actually kept constant. We are required to use the kinetic theory to explain why the pressure actually rises. So first and foremost, the keyword kinetic theory is trying to tell you not to use PV equals to nRT or PV equals to NKT to start solving the question. Okay, so for this kind of qualitative question, kinetic theory means you have to use all the assumptions to help you finally arrive at the right answer. So the way to look at it is, first and foremost, constant temperature implies that the root mean square speed of the molecule is actually the same. Okay, so therefore the change in momentum during the elastic collision is therefore the same. And the smaller volume, what it means is that the time interval between collision is actually shorter. So therefore there is actually a higher frequency of collision. And what this result is that the average force due to collision or the rate of change of momentum must be higher, leading to higher pressure. Okay, how come the rate of change of momentum is higher? Because recall that in this case, the root mean square speed being the same, the change in momentum is actually a constant. But recall that the way you find average force is actually dividing by the time interval between collision, which in this case, a smaller volume would actually reduce the time interval between collision. And this would therefore end up resulting with a larger average force, and therefore resulting in a higher pressure. So for the last example that I'll be going through, it is relating to the escape speed, which is something that you have already learned in gravitation. So here, you are given the minimum speed, which is the escape speed required by an atom at the top of the Earth's atmosphere to completely escape from the Earth's gravitational field. So for part A, what you are required to do is to solve for the temperature, and it is basically essentially just a simple application of the formula half mc squared equals to 3 over 2 kT. You are given the mass of the atom, so you do have that. You also have the velocity, which is just 1.1 times 10 to the power of 4. So basically, you only need to sub in the values and then Boltzmann constant, and then you can solve for T itself. For part 2, you're required to suggest why some helium can still escape the atmosphere even if the temperature at that region is still below from what we calculated in part 1. Now, the temperature at the outermost parts of the atmosphere can get really hot as well. Go Google something called the thermosphere, and temperature at that region can get as hot as 1500 degrees Celsius. But even then, it is still far below the temperature calculated in part 1, which is around 19,000 degrees Celsius. But you must remember, even at 1500 degrees Celsius, what it can tell me is that the root mean square speed is much lower than the escape speed. Okay, but recall that the atom is actually having a range of speed, and there might be just a few atoms that can still be at the extreme end where they are actually higher than the escape speed. So this few will still be able to escape. The idea is really similar to evaporation, where a pool of water on the floor is definitely at the temperature far below that of boiling point. But there are still a few of those molecules that is still having enough Ke to overcome the intermolecular attractive forces to evaporate. So this is the reason why even at a temperature that is lower than that of the value calculated in part 1, there will still be some helium atoms that can still escape because there will be some extreme helium atoms that is having some extreme velocity that's actually higher than that of the escape speed, and therefore they can escape. Now there's still one more work example with visible thinking on the next page, but I'll leave it to yourself to go through it because the working given is already very detailed. So therefore I'll stop here. I'll see you in the next video where we will start a new chapter.
Did you get any of that?
Sure, Bo,
Understand?
your online source of
Interesting physics lecture.